Hello students, in this video I will be going through the derivation of the properties of exponents. Let's take a look. So before I talk about exponents, I just want to maybe talk about how we work with numbers in general and how we have very cleverly come up with a way to write really long expressions using a shorthand. Let me tell you what I mean by this. So suppose I have three identical things, right, that I'm adding together, A, and A. So rather than writing A, and A, right, these three things over and over and over, okay, I can simply write as a shorthand 3 times A, right, or 3A. So there's an implied operation, okay, that's in between the 3 and the letter A here, and that's multiplication. Okay, so and then we can take this shorthand notation and pretty much extend it even further and say, suppose I have 2a plus 3a plus 4a. Okay, I can then combine like terms and say, well, through a lot of algebraic practice, you know that this is actually 9a, and the reason why it's 9a is because of this, right? Although you don't write this out because you already know what 2a plus 3a plus 4a is. That is indeed equal to 9a. But if you were to write it out, that's what this original statement is asking you to do, right? You're taking 2a's, add it with 3a's, and then add it with 4a's. Anyway, all of this is just shorthand for re-expressing, for trying to re-express an expression, okay? So let's say if we have another expression here in the form of exponents now, okay? So here, okay, this is an exponent, and I'm telling you that a raised to the first power is equal to a. We never write a to the first power because it's always implied, okay, that this is it's a. Anything to the first power is itself, okay? That's an identity. Same thing could be said about the multiplicative identity, which is, 1 times a. We never write 1 times a because it's always implied that this is equal to a. All right, so we're going to use this, okay, idea that a to the first, right, is a. So if I tell you, what if I wanted to figure out a times a, right? What would that be? Well, the notation, right, the 3 out in front is already taken. So the shorthand would not be 3a because that would tell the reader, okay, that you're multiplying 3a's here, and this is interpreted as a plus a plus a. So we need another notation. What exactly is that notation? Well, that notation would be a to the third, right? So this notation here, this exponent, is telling you we're multiplying a by itself 3 times. Here we're adding a 3 times. Here we're multiplying a 3 times, which is different from multiplying by 3. Okay, so try not to get that confused. All right, so we can also extend this idea even further and say, well, a squared times a to the third times a to the fourth, what would that be? Right? So this is not to be confused with 9a because it's not, because this 9 out in front means multiplication, right? So a to the second times a to the third times a to the fourth, it is interpreted as, once again, a times 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 a. That is, in return, is equal to a to the ninth. Again, the notation here, it's important that you be familiar and aware of this, right? The 9 out in front implies, okay, that we are adding 9a's together. This 9 as a hyperscript, okay, is telling us that we are multiplying 9a's together. All right. So this, okay, is actually, or this last step is actually a demonstration of something. So if you have exponents here, okay, and these numbers here, these a's, okay, this is what we refer to as the base. They all have common base, okay. If we have the same base, and we're multiplying these expressions with the same base, in return, what happens is we add the exponents. And this is the product rule. This is the product rule for exponential expressions. So again, one more time, if you have a, right, and a, which is the same base, and you're multiplying the two things together, you would add the exponents together. That's the product rule. All right, so suppose we have a quotient then. What happens here? Well, here in this case, I have a over a. Well, anything over itself is equal to what? It's equal to 1, right? Anything over itself is equal to 1. All right, that's good. What about if I have a over a times a? Well, this is the same thing as 1 over a, isn't that right? Because I have the same factors up in the numerator and denominator. I can reduce that to being 1 over a. Okay, that's good. So, you know, if I have a quotient, then what I'm telling you is you are eliminating common factors. That is one way of thinking about it. So what about in this case where the expression has gotten to be more complex, okay, where the numerator now is a squared and the denominator I have a product of a to the third times a to the fourth? Well, let's fall back to what we understand. The numerator, a squared, or a to the second, is a to the second. The denominator, right, I have a product that is equivalent to a to the seventh, because remember, we applied the product rule now, right? So I have a to the third times a to the fourth is equal to a to the seventh. Remember, this is a quotient. So what does this all mean? This is telling us we're taking 2 a's up in the numerator that are being multiplied, and we're taking 7 a's, okay, that are being multiplied by one another in the denominator. Can this fraction be reduced? I immediately see that we have common factors between the numerator and denominator, and that is a factor of a and a, or a squared. What am I left with overall? Okay, I'm left with, I'm left with 5 a's in the denominator, right? A to the fifth. So wait a second, let's just go back and reflect on this a little bit. A to the second over a to the seventh becomes 1 over a to the fifth. Or in other words, this is the action that has taken place, right? If I take the numerator, the exponent in the numerator, subtracted by the denominator, I'll end up with a to the negative fifth. And a to the negative fifth in return is therefore equivalent to 1 over a to the fifth. Right? Mathematically, we just arrived at this conclusion, like through deduction, okay? This is what we can conclude, that a to the negative fifth is in fact equivalent to 1 over a to the fifth. Now, in this demonstration that I just performed here on this slide, there's actually 3 things, okay, I want to point out. One is that step right there, that is the quotient rule. The quotient rule says if I have a quotient with the same base in the numerator as a numerator and denominator, the numerator and denominator having the same base, then what will happen is all we got to do is just subtract the exponents. We always take the numerator and subtract it by the denominator. Something else needs to be pointed out in this demonstration, and that is this idea of negative exponents. If I have a base raised by a negative exponent, which I do have in this case over here, a to the negative fifth, that is equivalent to 1 over a to the fifth. So this needs to be pointed out, that negative exponents is in fact the reciprocal of that base raised to a positive exponent. And there are 2 ways of expressing this. We can express this as a to the negative fifth, or a to the negative m is equivalent to 1 over a to the m, or 1 over a to the m. And this last step here is not as transparent at the moment, but just bear with me, okay? These these three things, okay, are equivalent. So again, negative exponent, I can rewrite it as the reciprocal of that base raised by that exponent. Positive version of it. All right, and then the third thing. Remember, I said there are three things, okay, that I can that we can conclude based on the slide here. The third thing is this: 0th power, a over a. A over a, right? If we apply the quotient rule, right? A over a is actually a to the first divided by a to the first, which is equivalent to a to the power of 1 minus 1. And last I checked, 1 minus 1 is 0. So therefore, a to the 0th is 1. Anything to the 0th degree, therefore, is equivalent to 1. So in the last couple minutes, we've arrived at the power rule, the quotient rule, negative exponents, and the 0th power. Let's take a look at the last situation. Well, what about power to a power? Can't we, do something about that? Yes. So if I have a to the third, and that is being raised to the 4th power, what does this really mean? What is this asking us to do with the number? So a to the third raised to the 4th is equivalent to a to the third multiplied by itself 4 times. Let's not forget about the basics of exponents. So a to the third raised to the 4th power is equivalent to a to the third times a to the third times a to the third times a to the third. An alternative way of expressing this is a to the 4th times a to the 4th times a to the 4th. What am I trying to get at here? How many a to the 4th are there here? There are 3 of them. So in actuality, this can be re-expressed in this manner. Right? Isn't that what the last step was? I'm taking a to the 4th and multiplying by itself 3 times. Alternatively, if all of these things are equivalent, how many a's are there altogether? That's right, there are 12 of them. I'm multiplying a by itself 12 times. So this is a demonstration of the power rule. The power rule says if I have an expression being raised by a power and then raised by another power, all I got to do is multiply the exponents together. Or we can actually reverse the order of the power that's being raised, right? Notice right now I have a to the m and then to the nth power. That can be re-expressed as a to the nth raised to the m power. You have no idea how convenient, okay, this is for when it comes to like manipulating expressions and proving other things, as you will see in future videos. All right, so here we are. These are the basics for the laws of exponents, or the properties of exponents. So let's try to summarize. Right? These are the properties again. However, there are 2 others, okay, that I want to discuss with you, and that is, and again, a direct application of what's already on the screen right here. Suppose I have this situation where now I have the power of a product, right? A to the m times b to the n, all raised to the power of L. What will become of this? How can we re-express this? If you combine the ideas of the power rule, right, with that of the product rule, but in this case here we don't have the same base, right? So we really cannot add the exponents together. So you cannot combine the product rule with this because we have different bases. The power rule, okay, if we have different things, okay, inside of parentheses there, all we got to do, this is we are going to multiply just the exponents. So a is equal to, a to the m times b to the n raised to the L power is equivalent to a to the Lm times b to the Ln. Similarly, if I have a quotient, power of a quotient, can you make a prediction as to what will happen here? The exponent, once again, will be distributed to just the exponents. This is equivalent to a to the Lm over b to the Lm. So these are all the rules, okay, that you will need to internalize. And I will encourage you not to memorize this verbatim, but to apply this in practice. Through practice, you will then memorize this. Okay? All right. Just one other word about the applications of these rules. Much like grammar, right, in English class, to help you sound more elegant, more eloquent. Same thing happens in the math discipline. So, you know how in English class you never write like a double negative, or you want to have your logic flow as smooth as possible. So same thing can be said in the math discipline, right? Math is just as much of a discipline of expression as English or art, okay? So in order for us to, when we are manipulating a mathematical expression, okay, through a rewrite or simplification, our final solution, our final answer, must always be left in the form of a positive exponent. If ever we are working with, let's say, fractional exponents, or expressions involving fractions, and those fractions having fractional exponents, then there should be no fractional exponents in the denominator. This very act is known as rationalizations. And I will go through in exercises demonstrating how we leave our final answer here. So this blue box, okay, that I am talking about right now, okay, this will be applied in practice in the next couple videos. All right.